Okay, this is kind of a big one. This is a bunch of more rules about arcs and angles and how they relate around a circle, and a bunch of coordinate stuff all in one. The coordinate stuff is there because next time we're going to do the one about equation of a circle. All right, so let's get to it with everything else. All right, so there's one about, we renamed it the interior vertex theorem, which I think is a pretty good name for it. This is about what happens when two, and the numbers that we picked here are really kind of crazy, when two chords intersect inside a circle. So we did inscribed last time, which, if you remember inscribed, that was if an angle is actually on, kind of on the circle. This is a little bit different. What if the angle is inside the circle? And what's kind of going on with the relationships around the circle that way? So if you have an angle inside a circle, like we do here at vertex B, there's two arcs that are kind of associated with being inside that angle. If you think about it, if the angle is, this angle at B, well, there's a vertical version of that, and those two angles kind of are, have in their mouth these two arcs. Well, it turns out that the measure of that angle in there is the average of those two arcs that I've highlighted. So that's what we say. Yeah, we add them together and divide by 2. We're going to get the measure of that angle. In class, let's do the proof. Or let's do the explanation of why that is. It's kind of cool. I won't even let the cat out of the bag. I'll let you think about it. Let's see if you can come up with an idea why that might be. But yeah, we'll talk about the explanation. And there's a bunch of different questions they can ask about this if this is the situation. Actually, here's some examples. I'll go straight to it. So here's this angle x that's happening between two chords. That's the same angle there. This one is kind of speaking to that arc, and that one's speaking to that arc. And what the theorem is saying is if I add the two angles and divide by 2, I'll get the measure of the arc. I'm cheating with my calculator here because I made a mistake last video. I got that wrong. Anyway, something that simple. So x is 62 degrees. That's all there is to it. The other way they might ask that is this way, where they give you the angle. You're supposed to realize, oh yeah, that's the same over here. And those, that 111, that's the average of these two here. So 152 plus this angle y divided by 2 is supposed to be 111. So if I take 222 and I subtract 152, that's a nice number. Y is going to be 70. All right. Then if the angle is on the outside of the circle, we still have a divide by 2 situation, but this one looks a little bit different. If you think about this angle that's out here and all of the stuff that's inside that angle, there's now 2 arcs associated with it inside the circle. There's this one here and there's this one here. And it turns out that the angle is half of the difference. So if the angle is on the inside, like this, the angles are half of the sum of the 2 angles, but if it's on the outside, like this kind of thing, it's half of the difference. And so that's being shown here. This 130.7 minus the 47 or so, divide that by 2, you're going to get the 41.86. And a couple different kinds of questions they can ask about that. What if they give you this? This is kind of the straight out of the theorem way to ask that. I can take and we will do the proof of this in class too. I'll make myself a note. 112 minus 41, and divide that by 2, I get 71, and then divide by 2, I get 71 halves, or it's not approximately equal to it exactly, 35.5. That's z. It's half the difference, and it's also true of tangents. So whether these are called secant lines, actually. That's 2 secant lines. This is a secant and a tangent. We call it the exterior vertex theorem because it applies whether or not we were talking about mixes of secants or tangents. It could even be 2 tangents. Whenever you have a vertex outside the circle, it's going to be associated with 2 angles inside it that are arcs of this, 2 arcs inside the circle, like that or like this. Those are the 2 arcs. So same thing applies. It's going to be this one minus this one divided by 2 to get that angle over there. So we'll just do x minus 48 divided by 2 is supposed to equal 23. So 46 is going to be x minus 48. 46 plus 48 is, drumroll, 94. Okay, hope I didn't make any arithmetic errors this time. So this is the end of all these kind of rules where we have angles and circles kind of relating with their arcs and finding measures and stuff. So what I decided to do was make one big page of all of kind of the pictures of all of the theorems in one place. And I added one. Actually, this one is not in the book anywhere, but it's kind of a nice one. It kind of wraps up about 3 little facts kind of all in one, which is that not only are the tangents perpendicular to radii, which is one theorem, but also the tangents that are coming from the same point to tangents of the circle, they are the same length. And if you draw the radii at the same, at these tangent points, you actually end up getting this little kite here, because those are radius at the same circle. So all that stuff is kind of cool. And then if you think about, since these two angles are 90, think about the angles that are left, the central angle, or you could think of that as the arc angle, those are the same, and how that relates to this other arc or this other angle on the kite. Those two angles have to be supplementary. They have to add up to 180 because of the 360 and the kite total, and 180 is already taken up by the 290s. So that's what this little sentence at the top says. Anyway, this is just, here's a review of all of the theorems and all of the rules from the entire unit so far. Sorry, when I printed these on half size, like this is really hard to see sometimes. So you could, when I do this, you can kind of pause through this video. You could see them maybe bigger, enlarge them on your laptop. This is what they look like if you wanted to kind of go back in there and write them down. Or I can make another printout, I suppose, if I need to. All right, here's the other part of the lesson today, which is all the coordinate stuff. The first part of this, I'm sure, is no surprise to anyone. Well, it's not supposed to be any surprise to anyone. We've kind of talked about this already, but this is a really long explanation of the distance formula. And the distance formula, I think we've kind of used from time to time so far. The distance formula is simply an application of the Pythagorean theorem. We have two legs here that have to be right angles because we're talking about length along x and along y in coordinates. So those will always be perpendicular. So you can always take x squared and y squared, and you'll get this distance squared. So feel free to memorize this if you want. It's not going to be on the theorem sheet because it's not a theorem. It's a formula. It's kind of a definition. It's really, again, just application of the distance formula. Yeah, so I'm not going to spend any more time on that. We will practice that enough in class, and it's going to be easy for most people. This one may be a little bit more of a surprise. Is the midpoint formula. If you need to find the midpoint between two coordinates, it's simply the average x and the average y. Yeah, that's going to be important when we start talking about circles, because we're going to be graphing circles, as I said, next class. So if we had a diameter or something, it's nice to be able to find the midpoint of things, because it might help us find the center of a circle and that kind of stuff. So. Yeah, and don't forget about slope. We still have slope going on. So let's do some examples. Find the midpoint and length of the segment from here to here. Okay, so midpoint they asked first. Let's just do that. Midpoint is the average x, which is 11 and 8 divided by 2, and the average y, which is 3 and negative 7 divided by 2. I'm going to mess this up. No, this is negative 3. That's easy. And 3 plus negative 7 is negative 4. Negative 4 divided by 2 is negative 2, I believe. And then the distance is simply the square root of the x space squared, like this kind of x distance, and then this y distance. I just squared those. The distance from negative 11 to 8 is 19, and the distance from 3 to negative 7 is 10. So that's all I'm really worried about. What's 19 squared again? I think I know that, but I don't want to mess that up. This is 361 plus 100. So this whole thing, whoops. Can't really see that anymore. Whoops. One more. Oh, why is this happening? I want to undo my. Ooh, I got all these cool things happening. I hit one little wrong button, and I can't even undo anymore. All right, 361 plus 100 square root. That's better. 461. That's an exact answer. Feel free to decimalize that if you want. I don't think it reduces. Okay, and then a couple more examples. Do I want to do these on video or want to do this in class? Let's do that one in class. This is not too bad. Okay, this one, now we're getting into this area called coordinate proof. Coordinate proof, I know, I said no proof second semester. That's true. Coordinate proof, I guess maybe coordinate arguments, coordinate demonstration, coordinate calculation maybe is a good way to say that. It's about putting coordinates onto geometric objects, or coordinatizing geometric objects in a clever and convenient way to be able to show relationships or measure things or kind of realize things. So this, of course, this isn't a proof. I think the title of the section might be coordinate proof, and I don't want you to get upset about that because I said no proofs. But yeah, it's the idea of creatively selecting how to position something on the coordinate plane to your advantage, which is a really cool skill to have. All right, so make this a right isosceles triangle. I keep hitting buttons accidentally and things are going all over the place. All right, so this has to be 45, 45, 90. So I know that like this distance has to be the same as this. Well, they tell me that this x coordinate is A, so that position right there is A, meaning the length has to be the same here. So this length is A. This length has to also be A. So this y coordinate has to be A. What else has to happen? Well, that's on the axis, so that's 0. This is on the axis, so this is 0. And of course, this is 0, 0, so that's kind of silly. So if you had those as your coordinates, you know you'd have a right isosceles triangle of length A for a side. This one is, what they told us it's a trapezoid. They gave us some coordinates, and they're saying find the coordinates of point G. Well, it's a trapezoid, and they tell us what's parallel. So they told us that this is parallel to this. And if you look around these coordinates a little bit, you realize that, hey, this is a midpoint here at F, because 9 is halfway between 0 and 18, and of course 8 is just this nice, well, it's halfway between 8 and 8, but it's also just a nice horizontal line, so it's easy to tell it's a midpoint. If this is a midpoint, and it says trapezoid. And it says, oh, sorry, this is the one that said we're parallel. If it's a midpoint and it's parallel, I know this has to be a midpoint. So this is a really long explanation of find the midpoint between C and D. Is what we're looking for, which we've already done before. I probably could have done this one in class. So the x is going to be halfway between 1 and 20, and the y is going to be halfway between 4 and 0, which is, I'll just leave that and call this 2. All right. Is that it for that page? Yep. Last page, this one, I'd like to do this one in class. This one is a little bit long, but I feel like I could have gone shorter on the last one, so I'm not going to do that one now. And show, notice it doesn't say prove, it says show that the line segment joining the midpoints of two sides of a triangle is parallel to the third side. In other words, if S is a midpoint, I'll do this one now. If S is a midpoint and T is a midpoint, how do I know that ST is parallel? So I can calculate these two midpoints. The coordinates of S are going to be at 2P, comma, Q. The coordinates of T are going to have to be, because I'm just going halfway between, right? Halfway from 0 to 4P is 2P. Halfway from 0 to 2Q is Q. Halfway from 6R to 4P, oh goodness. That's going to be 4, let me make this so I can see it. 4P plus 6R over 2 is going to be 2P plus 3R. And halfway between 2N and 2Q is going to be 2N plus 2Q over 2, which would be Q plus N. Now I'm trying to tell whether or not ST is parallel to AB. And so I need to find the slope of AB and see if it's the same as the slope of ST. Slope AB is the subtraction fraction. Let's do the zeros last. That makes life easy. This is 6R, and wait. Rise over run, right? Rise over run. This is N over 3R. I think I did that right. And then slope of ST, and I've got those coordinates right above me here. Which way is going to be easy? Let's do this way. Whoops, not that one. Do the y's first. Q plus N minus Q over 2P plus 3R minus 2P. Well, guess what? That's N over 3R. Yay! Life is good. They are parallel because the slopes are congruent. Okay, that's it. I will see you in class.